Hi, good evening, everyone. Today we'll be walking through one of the two fundamental things that we do in vehicle dynamics control, longitudinal control. And specifically, we'll be talking about ACC and CACC, so which is adaptive cruise control and cooperative adaptive cruise control. During the course of this presentation, I'll be running through the introduction and what are the motivations behind the development of ACC and CACC, the definition and conditions for the implementation of these controllers, what is the usual problem statement when it comes to developing a controller like this, how to evaluate the problem, what are the possible solutions that are in use today. There are a lot. We'll just be covering a few of them, just to give you an understanding of how it works. Then I'll be going to what is the state of the art currently in cooperative, adaptive, and adaptive cruise control technologies. And to round off the presentation, I'll just tell you, what are the potential career paths and job opportunities when it comes to talking about adaptive cruise control and cooperative adaptive cruise control. So let's start off with the introduction. So what is cruise control? I'm sure a lot of you have used cruise control. It's present in most modern cars. The way it's used now is usually in the latest cars, you'll all have adaptive cruise control. But where did it all begin? So cruise control was one of the first driver aid systems that was developed, like ever. It was developed all the way back in 1948. So this is when cars were still pretty basic. And essentially, it was a mechanical system developed by this engineer called Ralph Tata. His problem was the constant fluctuation in speed when he was sitting in the back, when he was being chauffeured. So what he decided was he just implemented a simple screwdriver motor to limit the throttle and hold it in one place. And he got what he desired. Essentially, what we saw in 1948 then was the introduction of level 1 automation. And that's pretty amazing because, I mean, we're talking about automation today, like the autonomous vehicle development, the 5 levels that SAE has defined. We were at level 1 in 1948. We just didn't know it. So now we move on to adaptive cruise control, right? What is the one which is more commonly used today? So ACC, or adaptive cruise control, is essentially advanced driver assist system, ADAS, which automatically adjusts the host vehicle speed to maintain a safe distance from the preceding vehicle. Many sensors can be used to implement ACC, but it's primarily radars. I mean, if you look at the image on the right-hand side of the slide where you look at the Mercedes-Benz, if you notice that the little plastic protrusion on the grille right under the Mercedes logo, that's where the radar is usually stored. If you look around these days, a lot of cars have a little plastic covering on their grille which hides the radar. It's a bone of contention for designers because it really ruins the design, but that's the most obvious place for it to go. And it's pretty simple in its implementation. So yes, a single radar which is used for implementing ACC. Now, before we go further, I'll just run you a quick video that Bosch has put out on the internet related to ACC. Let's just watch that video. I'll keep talking over the video just to give you a quick understanding of how this works. So basically what happens is when you're driving on the highway, I'm sure a lot of you are familiar, there's a lot of movement, like cars changing lanes, slowdowns. And so you have to focus all the time. There's a lot of concentration that you need to have, especially if there's like a vehicle which stops right in front of you. So you're like constantly on edge. So the whole point of the development of the system is to reduce the pressure off the driver. Essentially the same thing that Ralph Tata did back in 1948. We're still doing today. We're trying to make the life easier for a driver. How it does it is there's a radar in the front which is constantly broadcasting a signal trying to look for vehicles. It's essentially tracking vehicles in front of it. It can pick up vehicles essentially the way Bosch long range radars work today. They can pick up vehicles in your lane and the vehicles in the side lanes as well. And it's pretty simple to use too. If you've used it, it's pretty simple. You just have to pull a button, a lever, something where you just ask cruise control to turn on. And for adaptive cruise control, like the showing in the video, you can just, press a few buttons and set a distance too. So assuming you're in a place where traffic is, more spaced out, you can maintain a big distance. But if you're scared that somebody's going to try and cut in because you left a lot of space, you can also reduce that distance. And essentially, as the vehicle in front slows down or speeds up, you keep up, but you'll never exceed the speed that you have set, which means that you're always comfortable. So even though you are expected to maintain control of the vehicle, it still lets you relax when you're driving. So as you can see in this video, whenever a vehicle is suddenly moving into your lane, your vehicle will slow down automatically. Essentially what happens is the radar controller sends a signal to the ESP controller in the vehicle, which sends out braking force to all the 4 wheels and slows you down. I mean, it seems pretty simple if you look at it right now, but it's taken a lot of years of development to get here. And the way it works today, if you use a single radar, it works from about 30 kilometers an hour all the way up to 200 kilometers an hour, which is quite impressive because at 200 kilometers an hour, you're covering a lot of distance really quickly. So to make sure your vehicle is able to stop in time and respond, these sensors work really quickly. Another thing that they do with this, another application of ACC is in something called stop and go ACC. So how stop and go ACC works is, this is something that works below 30 kilometers an hour. So essentially, say you're in stop and go traffic and you are tracking a vehicle in front of you. Essentially, what it does is it will bring your vehicle to a complete stop when the vehicle in front of you comes to a complete stop, and the ACC does not turn off. Again, these are things that seem pretty simple, but these are unheard of. Like even 15 years ago, 20 years ago, these technologies were not in place. And now they are starting to become more and more commonplace. And it makes the life of a driver so much easier. I mean, imagine if you're in stop and go traffic in Bombay or Bangalore, where you could just, turn on your stop and go ACC and not have to worry about constantly stepping on the brakes. The vehicle does it for you. You are monitoring. Again, this is not level 5 automation where you can, read a newspaper or play on your phone, but at least you're not stressed about having to jump on the brakes at every instant. These are amazing technologies now that we started to take for granted, but if you go into the background of these, they're really impressive. There's something else which ACC can do, something else which I find useful, which I have actually had the opportunity to use in the past. It's called AEB. AEB usually uses more than just one radar. So like they've shown here, you can use 2 radars. It's usually combined with other things like cameras. Maybe you have like a close range ultrasonic sensor. We use something called sensor fusion to put it all together. And it can give you more than just tracking the front vehicle. And it makes your driving experience even easier. And after this, we'll quickly run to another video where I'm showing you what Tesla's managed to do. I mean, this is something which a lot of car manufacturers do. But Tesla, because they're recording all the time, they're able to capture some really great footage of how this works. Okay, here they've shown the driver press the brakes, but in a lot of applications, you really don't need the driver to be pressing the brakes either. So let's hop on over to the next slide. So essentially, this is a video from a Tesla. As you can see, they're going pretty fast. They're going about 114 kilometers per hour. So that's about 70 miles per hour. They're driving, and I'll turn the audio on because normally when the ACC AEB kicks in, the automatic emergency braking, the car usually gives off an audible warning to let you know what's happening. Because I mean, otherwise it's pretty surprising if your car stops on the brakes itself. So these are like a human machine interface, a feature to tell you exactly what the car's doing. So let's start this video. It's a bit gruesome, but rest assured nobody got hurt. So although there is an accident in this, but no people were hurt. So in this video, if you heard it, I'm going to run it again quickly. If you watch it again, the Tesla beeps before you can see the car in front. Before the black car is visible to the driver in the Tesla beeps and starts applying braking because it's noticed that the vehicle in front has started stopping. So the way it does it is using radar. So radar essentially is not a line of sight sensor the way a camera is. A radar can bounce off signals even off the road to pick up the vehicles in front. So it's actually picking up more than just the vehicle in front. So let me just run that for you quickly. If you just wait for the beep, you'll see the beep, and then after that you will see the red car in front start braking. So our radar in this Tesla responded faster than the human in this red car because you'll see the brake lights go on, but that's after the beeping in the Tesla. So let's see that again. So it's pretty amazing. I mean, this technology saved the people in this car from having an accident. Now just imagine if every car on the road can have this technology incorporated into them. You'll never see accidents like this again. Yes, so now let's move on. What are the advantages of ACC? I mean, yes, obviously there's blatant safety advantage. There is a comfort. But there are other advantages too. There is a massive increase in fuel economy. So there's a little graph that I've picked out from a research paper on the side where you can see when there's conventional cruise control as compared to ACC, how many driver inputs are there. So you can see there are significantly more driver inputs during cruise control. I mean, for one, there is no brake application during regular cruise control. You will be traveling at a constant speed. So if the vehicle in front slows down and you press the brake, then you need to use the accelerator pedal to go back up to speed. ACC does all of that for you. So it makes your life a lot easier. Safety, comfort, and economy. I mean, these are 3 big reasons why you would buy a car in the first place, right? For safety, comfort, and economy. And ACC delivers on all 3. And I mean, it's not just a promise. It's something that we have seen. And the response time of an ACC system being faster, again, it was in that video. Here you can't even see in the Tesla, you can't even see the vehicle in front, but it still managed to brake. On the other hand, the maroon vehicle who was right behind them could only press the brakes and turn away. So now there are some limitations to the system too. I mean, it's a great system, but it really can't do everything. So The main problem is ACC is a reactive system. It can only respond to inputs that it sees from the vehicle in front. Now, I mean, it doesn't seem like a big limitation, but you have to realize that a big traffic jam, which is happening, right? It can't read the state of the whole traffic flow. It can only read one vehicle in front. And I mean, although it doesn't seem like much, but if you put it in the bigger picture, when we get to ACC, you'll see what I mean by having that limitation of only being limited to one or two vehicles in front. I mean, you can develop ACC further by providing it more information, but the more information you put into it, you actually move into cooperative adaptive cruise control technology. And sensor fusion becomes complicated, more sensors get added, costs get added. So mostly because of this cost factor, you will see usually it's just a radar being used for ACC, and anything more would then become used into other technologies. So yes, moving on to the new where we are right now, where we're heading in the future, it's cooperative adaptive cruise control, or CACC. This is also called platooning, especially when used in the context of commercial vehicles and trucks. You'll see pretty often. You'll see like a bunch of trucks which are moving. I mean, if you remember the movie Interstellar, they've actually used it there too. They have these autonomous trucks which are driving, and they're all driving in like fleets. So platooning has a bunch of advantages. We'll go through them in a little bit, but basically, with the development of vehicle to vehicle and vehicle to infrastructure, it's actually called V2X. The development of V2X communication has meant that ACC has become smarter than ever before. What I mean by smarter than before is you are not just looking at the vehicle in front, you are looking at the entire traffic flow in front of you. Your vehicle is able to read signals from the lead vehicle in your platoon, and that makes traffic flow so much better. It's essentially an extension to the ACC idea, but it uses so much more information, and you can create a feedback loop where you're not just tracking the lead vehicle velocity and acceleration, but you're tracking the inputs that are being sent. So you can respond in real time to a braking or an acceleration event being generated by the vehicle in front. Using the preceding vehicle's feed-forward controls, using the preceding vehicle's inputs in a feed-forward loop is so much more beneficial to the smoothness of the flow of the vehicle and increases comfort and safety and fuel economy and all those other things by a lot. So what is the motivation behind CACC? We've all experienced gridlocks. And something we don't realize is that gridlocks flow back. It's a pretty organic way it flows. If you notice that little video that's playing on the right hand side, you'll see that one of the vehicles decides to change a lane at the last minute, and it forces the driver behind him to apply the brakes. Now, as you notice, this traffic flows backwards, and people are slowing down miles down the road without knowing what caused it in the first place. I'm sure we've all seen it. You're driving, suddenly there's a traffic jam, and then you look around trying to figure out, what slowed down. There's nothing to have caused this traffic jam. But in actual fact, the traffic jam may have happened miles ahead of you without you knowing, right? So these phantom jams can be avoided. So if you have V2V communication, right, or V2X communication, you know what's happening in front and your vehicle can respond accordingly. Again, this requires all the vehicles on the grid to be involved, to be sharing information. But once it's there, we will avoid this completely. There is no scope for phantom jams anymore. So you'll constantly be flowing. And essentially, that's why they like to use it in commercial vehicles, because commercial vehicles are big, heavy vehicles. So you want to avoid acceleration or braking as much as you can, because it takes a lot of energy to get them back up to speed. So something like CACC really helps from a larger point of view, from an infrastructural point of view. It increases flow throughput. So basically your 4 lanes of traffic can accommodate that many more cars. I mean, in autonomous applications, this is pretty necessary when it comes to autonomous applications in the future. Right now, CACC is enough, but if you look at any expert, if you listen to any expert on autonomous future, they will all talk about all vehicles being involved in the autonomous experience. I mean, nobody wants to have a mixed environment where a human and an autonomous vehicle is driving together, because as we've seen with Waymo's car crashes that have happened, they haven't had a lot, admittedly. They've been doing some really good work, but they have had a few incidents where it has not responded to a human's behavior, because it can't expect human behavior the way we can. I mean, there's only so much that sensors can do in real time. So I'll just run through another demo. This time I'll let the audio play. This is by the Federal Highway, this thing in America.
Station Joint Reserve Base for Oak Grove to test some of the connected automated vehicles that we've been working on over the past year and a half in the Federal Highway Administration. This application is designed to improve mobility and safety for freeway travel using off-the-shelf commercial technology available on vehicles today. One of the earlier research projects we had in the Exploratory Advanced Research Program looked into cooperative adaptive cruise control, and the benefits were actually very significant. We looked into it in microsimulation, and we can kind of project benefits, but really we're running these experiments to see, are these benefits real?
So the way the technology will function is individuals now set automatic cruise control. So they're going to set the speed or the distance that they want to travel behind the car in front of them. Those technologies are going to be connected so that the cars will be communicating to each other, so they know when they're going to be speeding up, when the lead car is speeding up, or when that lead car is slowing down. And the car behind it won't have to wait until it sees that speeding up or slowing down. It will know it because the car in front is going to be communicating to it.
The cooperative piece comes from not just the vehicle in front of you, but multiple vehicles in front of you and around you. So if one vehicle starts slowing down, all the vehicles in the platoon will at least be prepared to slow down, if not start slowing down already.
What makes the development of this technology possible now is a combination of communication capabilities, high-speed, real-time communication, the ability to do data collection in a real-time environment, and to process that data.
So when he's hitting the brakes, are we closing the gap?
Not particularly. At least not immediately on the way.
In each of the cars, we have a compute platform that manages the entire system and also manages the throttle and brake. We have a centralized positioning and timing system, so all the systems in the vehicle have the same position information and timing information. We have, in this case, the algorithm that actually controls the speed of the vehicle based on the factory radar system, as well as a specialized basic safety message, or BSM, that all the vehicles are broadcast.
So we're trying to make the investment now to understand and learn how these algorithms are going to work together so that we can share what we know with other industries in order to affect the method in which these vehicles are actually going to operate on the highway.
So what we do is we'll do a test run. We'll collect data from that test run. We'll also obviously monitor the gap between the two vehicles, detect whether the following vehicle is speeding up or slowing down too soon, make sure we're maintaining a correct gap to the lead vehicle, and then we go back to the lab. There's a lot of test, review, update the code, test, review, update the code. That's kind of the cycle we're in right now.
As roads become more expensive and as our highways become more congested, we have to start looking outside the box for alternative means using technologies that we have today to address the congestion and mobility issues of the future. And that's why we're involved in what's known as automation.
So we think that the federal government has a role in doing the initial research in terms of the feasibility and looking at the different technologies that are needed to make this happen.
And to work with standards-making organizations in a way that will allow for this equal playing field. The technology is agnostic, but the standards are there such that people can compete with applications using the same technologies.
Yeah, so our research really isn't about necessarily bringing a specific product to market. It's more bringing the technology to market and sharing our results with everybody so we have a consistent system across manufacturing, across platforms.
So we're looking at it from a feasibility standpoint. We are also working with the auto manufacturers so they're able to take the results from our research and development and then integrate that into their vehicle production.
So case in point, traffic signal control. If I'm an OEM, I want to sell a car that's automated. If we in the federal government show them the benefits of an eco approach and a glide through that traffic signal that works, all of a sudden, we're helping to create a demand, and the public is going to demand that of the private sector.
Really what the federal government's main role, if you think about it, is to kind of spur the market and to make those initial investments in showing how this technology can make improvements, but also then providing guidance to the states on how we can deploy this nationally.
So as the federal agencies responsible for providing the states with a large amount of their construction money that they use to expand highways, we want to provide them research results and tools for them to have more effective investment of those federal dollars.
I hope for in the work that we do is a bringing together of different communities that can share their expertise in a way that the whole is much greater than the sum of the parts. We are creating the initial steps for the deployment of revolution in the way we operate our transportation.